Good day, everyone. We are just going to give another 5 minutes just so that the attendees that are still rolling in can join. So we'll start about 4:05. Okay, everyone, we're roughly at just over 70% of the participants. So good day, everyone. I'd like to extend a warm welcome to all the attendees who joined us for this afternoon for the SAIEE webinar on large motors and drive systems. This is part one of a two-part series. I am Theodore Visser. I am Vice Chairman of SAIEE Mpumalanga Centre. I'm an electrical engineer for Broconics. And the webinar today will be presented by Kirk. He's the Senior Manager for Engineering and Projects Automation Division of Zest. Kirk has a diploma in electrical engineering and has more than 12 years of experience in the field of medium voltage drive systems. Kirk is presently the Engineering and Project Senior Manager at Zest Automation Division, formerly known as Shaw Controls. So I would just like to remind all attendees that they should ensure the volume is turned up on their devices. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. All attendees are encouraged to ask questions via the questions panel on the GoToWebinar interface. The panel is located within the control panel. By default, the control panel is located on the right-hand side of your screen, unless you've moved it since. So the chat function won't be available to the attendees, but you can use the question section. A recording of this presentation will also be made available on the SAIEE YouTube channel, SAIEE TV. The recording will also be made available on the SAIEE website under the events drop-down menu in the section past events and webinars. So this page is regularly updated, so please ensure that you check back as often as possible, not for only this webinar, but for other webinars as well. And please subscribe to the SAIEE YouTube channel for more uploads. A certificate of attendance will be issued by tomorrow for all attendees to claim their CBD points. And with that, I think, Kirk, I'd like to pass on to you.
Thank you very much, Theo. All right, thanks, Theo, for that introduction. Really appreciate it. Just a couple of things. I'm very accustomed to doing live presentations with audience participation. The webinar the webinar approach is a little new to me. I don't read my presentations, so forgive the odd stutter and stumble. I think it's a little more authentic to go through it that way, though. So let's jump into it. The presentation title is Large Motor Drive Systems. Just to define a large motor drive system, when I'm talking drive in the context of the title, it doesn't necessarily mean a variable speed drive. It can mean it actually means it can be applied with any other indirect starting device, or it could just be a motor on its own. But really, we're going to take a holistic view of the different motor types and the different starting types, hence the term drive systems. Just to define a large motor drive system, in fact, we're talking about large motor industrial drive systems. So to define that, we would be talking large megawatt ranges, let's say for the purpose of this discussion, more than 1 megawatt, and definitely more than 1000 volt, typically 3.3 kV and above. So in the agenda, just in broad strokes, we will look at typical large industrial motors or drives, and we specifically related to how they are affected by certain things. So we will look at different load conditions and different load applications. We will then, number 3, we will look at the varying impacts on the power supply systems of different motors. These two subjects are very well and very commonly known about. I'm not going to spend too much time. The main reason we're covering those topics is to set some loose general categories, which we will use in more detail later in the presentation. Then in section 4, we look at the different motor technologies available in terms of construction design. And there we look at some typical motors in both induction and synchronous machines, and we just do a very high-level comparison of the different types. Then in section 5, we're going to narrow down to a specific motor design for low inrush currents, direct online starting. It'll become clear later, but that's an alternative to using a standard direct online motor with an indirect starting device. That's how we design a machine to reduce its starting current, which can be used in certain applications. Then we'll look at large industrial drive systems, and then optimize solutions for starting. And then we look at some novel ways to use VSDs in some unique circumstances where possible. All right, to jump into a typical large industrial drives. So to set the tone, we talk about induction motors. We've drawn a scale here of megawatt versus speed. In general, induction machines would be useful in applications of low to medium power in high speed, that is low number of poles, and right up to medium power in low number of poles. On the other side of the spectrum, synchronous machines find their applications generally in very high megawatt ranges, and they are particularly useful in high megawatt low speed applications. That's very high number of poles, anything 20 poles and above. And then we have this area in between where we can really choose to use either a synchronous or an induction motor. Both would be capable to operate within this range of applications. The choice here comes down to whether a synchronous machine is needed for a specific purpose. That would be to adjust the power factor for reactive power compensation, or if the process specifically demands or requires a synchronous machine. When we talk about large drive systems, these are generally not off-the-shelf solutions. These would be motors that are specifically designed in most cases for a certain load or a certain application. Unlike a low voltage motor, which would generally be bought off the shelf and needs to already be technically compliant to a large range of loads and applications, in the large motor solution environment, this is not the case. We would need to, or we do design the motor more specifically for its application. With that being said, there's some critical design information that is needed to correctly specify and supply a large machine. These I've just divided up into categories. So we need to know the nominal torque. This would be the rated continuous torque that the motor is needed to produce to run the load in a steady state condition. Then we need to have the torque curve characteristic of the load and of the motor, and ensure that the motor is able to accelerate the load. And this is more of a dynamic analysis. Then we need the moment of inertia. This is useful in calculating the acceleration time and making sure that thermally the motor is able to accelerate the load without exceeding its thermal rating or capability. Then we need to know the starting torque requirement of the load, and that will determine a lot in terms of the design of the motor and whether we need to apply some special design as opposed to a standard squirrel cage machine. Then number 5, the torque in the end of load acceleration. So when you ramp up a motor, when you get to full speed, in most cases, in most applications, you would have the full load applied from the beginning of the acceleration period right up until the end point when the motor is running at full speed. However, there are some applications where this is not necessarily the case, and we will discuss those in more detail, because there's some fancy footwork that we can do there in terms of some optimized starting techniques. And then the last thing is the industrial process. This is the actual application data. For example, is it in a safe or a hazardous area? That can be a determining factor also in how we design the machine. On your screen, we're showing some typical load characteristics. This is just a simple case of a parabolic load curve. And I've drawn two case scenarios there. One is the red curve. That is a parabolic load curve accelerating from 20% starting torque, you can see on the left-hand side there, And as this load is accelerated, it gets to 100% nominal torque when we reach full speed. However, that does not necessarily always need to be the case, and that's why I've drawn the blue curve. In some applications, you would accelerate the load, and when you get to the end of acceleration point, when you're at full speed, the full load is not yet applied. That full load can be applied by other means, for example, through the activation of a clutch or through the actuation of valves or vanes in the case of a fan, etc. I think that's a pretty simple concept that everybody understands, but we can use that, and you'll see later why it becomes useful in certain optimized starting methods. So just remember those two curves. Right, now we're going to loosely define, just for the purpose of classifying load conditions. This is not as per any standard. This is just for the purpose of this discussion to set some typical load characteristics so that we can easily summarize the different options for motor design and starting method a little bit later. So we've defined here light starting duty as an application where the load inertia is less than or equal to the motor's inertia. That's essentially the motor rotor inertia, where the starting torque required by the load is less than or equal to 40% or 0.4 per unit value of the nominal rating of the motor, and where you have an end of acceleration load torque of 60% or less of the motor's nominal rated condition. Then we define a normal start duty scenario. We define a normal start duty for the purpose of this presentation and this discussion as load inertia less than or equal to 3 times the motor's inertia, starting torque required to get the load away of 75% of the nominal rating, and end of torque acceleration of less than or equal to 100% of the nominal rating. Right, then we define heavy start duty as high load inertia greater than 3 times the motor's inertia, starting torques that it could exceed 75% of the nominal rating, and where end of acceleration could also possibly exceed the nominal rating of the machine. A good example here would be a ball mill or a crusher, where you have a large inertia and you can there are short time overloads required both during starting and possibly during operation of the load. And then the final classification is applications that require speed control or torque control. And in this case, the example would be needing to use a variable speed drive in continuous operation or directly connected to the motor permanently. Okay, so we've defined the different load conditions. Now we're going to define some or classify the motor design in terms of its impact on the power supply. This will also be a very common theme to most people. We're just setting some classifications for ease of comparison later. So we can define the starting of large motors, or we are defining them in 3 levels of impact on the power grid. We define, in this case, low impact as a starting current. Remember, the impact on the power grid is affected by the starting current of the machine. In this case, we are defining low impact as 0 to 3 times the nominal rating or the nominal current rating of the machine. 3 to 5 times is medium impact, and 5 to 8 times as high impact. Low impact would be, for example, a standard squirrel cage induction motor, but used in conjunction with a VSD connected to it. Another example that's quite expensive if you are only using it for starting to have a low impact on the grid. Makes better sense in most cases to use a VSD to give you the low impact benefit, but as well as where you need speed variation. However, there are cases where a VSD does make sense for starting only. Again, we can do some fancy footwork in optimized starting, where we use that blue curve where the load, does not accelerate to its full load condition at the end of acceleration, to try to bring down the cost in certain applications. Another example of low impact would be a slip ring machine with a rheostat attached to the rotor during starting. Then we have a medium impact. This would be an example here, would be a low inrush current motor. This is a standard squirrel cage induction motor that we apply some special design considerations to, or design changes to, in order to reduce the starting current of the machine. The advantage with that is you don't necessarily need to use an indirect starting method attached to a standard motor. We'll examine that in a little bit more detail later. And then our final classification is high impact on the power grid, and this would be a standard design squirrel cage motor or a synchronous machine. All right, let's get to section 4, electric motor technologies. See, I'm just trying to hide. Do you have any idea how I can hide the little pop-up screen?
Kirk, you can just minimize it.
Sorry, just give me a moment. Okay, there we go. Apologies for that. Okay, so we're going to take a look at some of the typical motor designs. The first and most common one, and by far the simplest in terms of construction, would be the squirrel cage induction motor. The fact that it is the simplest to manufacture gives us some specific advantages using this type of machine. It is inherently robust. It is reliable. From a CapEx and OpEx point of view, it is comparatively the lowest of all the motor types to install. It undoubtedly has the smallest footprint, a reasonable efficiency, a pretty good efficiency, and it can easily be used with other starting methods, for example, VSD or other type of indirect starting method. Some disadvantages: in the standard design squirrel cage machine, high starting current is unavoidable in direct online condition, and it gives reasonable starting performance, but for very high inertia loads that need a high overload, generally the squirrel cage machine on its own is insufficient. Then we look at a wound rotor induction machine. This is also an induction motor. However, we replace the rotor with a wound rotor, and we link it to an external rheostat resistance in order to change the resistance of the rotor during the startup process. This allows us to increase the starting torque. In fact, if the rheostat is dimensioned correctly, the limitation here during startup is only limited by the breakdown torque of the machine. And here you also have an effect where the starting or the torque of the machine is directly proportional to the torque of the load, and the same applies to the current of the machine during startup. One interesting thing to consider here is the use of brushes. So from an OpEx or operating point of view, there is some maintenance required, some brush replacement. And one additional thing to think about is the dust buildup. So our service team went to site and attended to a slip ring machine in Saudi Arabia, very, very large slip ring machine. It had multiple sets of brushes per slip ring. I think 11 brushes per slip ring. And this machine was not equipped with a brush lifting device. In other words, the brushes were fixed. So after startup, they did not lift or remove the brushes from the circuit. They operated this continuously, brushes fixed. The brush wear was approximately 10 millimeters per 1,000 hours, which seems pretty reasonable. That's approximately 10 millimeters every 40 days. But the issue here was less so the replacement of the brushes and more the amount of dust buildup in the slip ring compartment. They were installing special filters to capture the dust, and every few days they needed to clean the dust out of the filters. I'm going to demonstrate on a video. This was after a few days of carbon dust buildup blown out of the filter installed in the slip ring compartment. With that in mind, it's common practice historically, slip ring motors would be supplied with fixed brushes only, regardless if they were being used for speed variation or not. It is now common practice to install a brush lifting device so that after starting, the rotor gets short-circuited and the brushes are able to be lifted, avoiding a lot of this problem of dust buildup. Right, then we get to the synchronous motor technologies, the first of which is the cylindrical laminated pole. This is arguably the most versatile and fit for purpose synchronous type, if a synchronous motor is required for an application. So it would make sense from our perspective to first analyze if you can utilize a cylindrical synchronous machine, a cylindrical laminated pole design, before you start looking at other designs, since this construction is the most simple to manufacture and gives some additional advantages. So one important thing to consider with this design is that the rotor construction, being perfectly cylindrical, creates a uniform air gap between the rotor and the stator. Also, the damper cage, which is the squirrel cage construction, which allows this motor to self-start, is also symmetrically placed, embedded into the excitation winding. Those two facts give this synchronous motor an advantage that because the air gap is constant, you don't get an oscillatory torque known as reluctance torque, which is quite common in other synchronous motor designs. Just to show you a little bit more detail on the construction, the cylindrical rotor is composed by a non-segmented laminated core mounted on the shaft. The field winding is manufactured with insulated rectangular copper wires. The coils are inserted into coil slots and fixed with proper wedges. The cage bars are placed into the rotor slots and short-circuited at their ends by short-circuit plates. The next type of synchronous motor that we're going to discuss is a salient laminated pole design. You can already see just by looking at it, we do not have a uniformly distributed rotor winding design, and so your air gap torque is not uniform. And here you need to do an additional analysis because of that, the oscillatory torque created by a non-symmetric magnetic circuit. And so it's just an additional due diligence that needs to be done on these machines to ensure that we do not have a torsional vibration issue inherent to the design. These kind of synchronous machines, at least, are very common in the high power, slow speed, in other words, large number of poles designs. This particular example is a 9.2 megawatt 20 pole design. However, they can also be constructed in high speed designs you're looking here now at a 4-pole design of the same construction type. This just gives a little bit more information on the construction of the salient poles. Essentially, they are separated, the poles, and you can see nicely on this photo here the squirrel cage or damper winding that's used only during startup of the machine is constructed on the outside surface of the pole shoes. Right, I mentioned that the synchronous motor designs, the two that we've just discussed, these motors, unless you use a pony motor or some kind of an external starting method, these machines are unable to self-start. And so in order to self-start them, that you need to incorporate a squirrel cage into the field winding, into the excitation winding, to allow induction startup like a normal squirrel cage induction motor would start. And this slide just shows the construction of the starting cage that is essentially built in and incorporated in the rotor design. Then we move on to a salient pole design, but this one has a solid integrated pole. This is a very expensive machine. If you look at the construction, if you look at the picture, this rotor is essentially machined out of a single solid block of steel, both the shaft and the pole shoe. And so you can imagine the price of this machine. So it would definitely be worth checking if you can get away with a cylindrical pole design before you start looking at this design. This has some advantages in that you do not need a separate damper cage to start it. It is self-starting as it is. That is because enough induction is created on the pole shoe surfaces to overcome its own inertia and get this motor away. In addition, it has an advantage of having a very high starting torque. So for very high overload starting or high starting torque loads, this is a good synchronous motor option. Just to show you the physical construction, so you can see the shaft, the rotor, and the pole shoes are all machined from a solid piece of steel. One additional consideration for these type of machines, the solid integrated pole shoe design, is although they have a high starting torque, they do get a lot of heat buildup on the surface of the pole shoes. And so for multiple starts, we need to take that into consideration to ensure that the rotor does not thermally exceed its own capability. This just gives some additional detail to the manufacturing process. So essentially a solid construction, machined, and then the field windings, either copper wire or copper bars, are inserted between the pole shoe and the shaft. This is the rotor design for a 4-pole machine. And the next picture is the same construction type, but for a 6-pole machine. These machines are unsuitable for low-speed applications. They find their place more in higher speed applications where high starting torques are required. Yeah, we're just having a look at the heat buildup during a start, during one start of these machines. And this is due to high eddy currents that are induced and concentrated at the surface of the pole shoes. The graph compares, you can see the red dotted line is the starting torque or the typical starting torque curve of a laminated salient pole design, and the blue curve is the starting torque curve of the solid integrated pole design. And you can see a much higher starting torque is available from this machine. Because the cost of the solid integrated pole design is so high, there are alternatives that have been proposed or that are being manufactured, which have this similar characteristics but a little bit cheaper to manufacture. This is an example of one of them. So yeah, instead of having one solid block and machine from that one solid block, the pole shoe is bolted on as a separate piece of steel to complete the construction. One of the issues with this design is that the eddy currents are exacerbated even more so than on the solid salient pole shoe because of the additional edges of the bolts and the holes, and that produces an extreme thermal increase during starting. In fact, the surface of these pole shoes can reach temperatures of 500 to 600 degrees during starting. So for applications where you need multiple starts, this synchronous motor design is a no-go. Where you start this machine and it runs continuously unless there's a problem, this is a synchronous motor design that you can consider. This is just an example of a smaller cylindrical synchronous machine. Okay, so just to tie this all up, we're doing a comparison here of the different, we're looking at the load conditions versus capex. So what are the most expensive machines to install? So quite obviously, in light starting duty application, a standard induction motor would be the cheapest installation from a capex point of view. And then you can see the synchronous machines get more expensive from a cylindrical synchronous machine up to, and then a salient laminated pole, and then a solid laminated pole design. In the normal starting duty, the same principle applies. High starting duty, the same principle applies. Induction motor would obviously be on the lower end of the spectrum. For high starting duty, an induction motor is not always the right option because it does have a limitation in terms of its starting torque. A wound rotor induction motor can solve this problem by adding resistance into the rotor to increase its starting torque. And then for speed variation applications with VSD, of course, the induction motor with VSD is the least expensive. Just to chat about this, a synchronous motor on VSD application. In most cases, a synchronous motor would be used where you need to adjust the power factor for reactive power control, where you want to put reactive power back into the system to increase your overall plant power factor. When you can use a synchronous machine on a VSD application or with a VSD. However, if it is permanently connected to the VSD, it is the VSD that controls the power factor and no longer the synchronous motor. And that power factor would hover close to unity, but would be in the region of 0.97 lagging. So it is not necessarily a practical solution to use a VSD started and operated synchronous motor. It is possible to use a VSD on a synchronous motor and bypass the VSD. If you want to use the VSD for starting, you bypass the VSD after the synchronous machine has started, and then you can operate the synchronous machine to give you reactive power control. Right, then we do the same or similar summary of starting current versus capex for the different impacts onto the power system. So the lowest impact designs would be an induction wound rotor induction motor, coupled with a rheostat, that would be the least expensive option for low impact to the power grid. A VSD, if not used for continuous speed variation, is quite obviously a lot more expensive. However, you do get the added advantage that you can use it with a squirrel cage machine. And so from an OpEx point of view on the machine, on the motor itself, it is reduced compared to a slip ring machine. And then, as I mentioned on the previous slide, we can use a synchronous motor in conjunction with a VSD. Obviously, this becomes a very expensive solution, and it is your reactive power control is very limited because it is in fact now controlled by the VSD and not by the synchronous machine. Okay, then in the medium impact zone, of course, we can use standard induction motors coupled with indirect starting methods such as reduced voltage starters, either star delta starters or soft starters. Another option, which we're going to examine in a little bit more detail shortly, is this low inrush current design motor without any additional starting hardware attached. Is just an adaptation of the design of the machine to enable us to reduce the starting current. And then in the high impact zone, a standard induction motor direct online is the cheapest or least expensive from a capex point of view. And then of course, if we need synchronous machines, it becomes a lot more expensive. I think the takeaway point here is, depending on the requirement of the power network supply, if you can get away with a high impact start from a large direct online motor, it is a robust and inexpensive solution. All right, let's unpack the low inrush current design machines in a little bit more detail. So let's just define some requirements of where we can use or where we can apply a low inrush current design motor. In essence, this is just an alternative to putting in some other starting device. It's really designing a standard squirrel cage motor to reduce the locked rotor current or the starting current to a medium impact level of starting current. It can be used in light starting duty applications only, because if we need a high locked rotor torque, it is difficult to get a high torque during startup and get a low starting current. You'll see that those two parameters are inextricably linked. So just as a reminder, we defined a light start duty as the load inertia being less than or equal to the rotor inertia of the motor. The starting torque requirement 0.4 per unit of the motor's nominal value, and an end of acceleration torque less than or equal to 60% of the nominal rating of the motor. So this is used in light application duties or light load applications, for example, compressors, and it's used where, or it is useful where your end of torque load is not your final load applied. So once this motor reaches its full acceleration, only then is the load applied. For example, on a compressor, starts against an open valve, so there's no back pressure, and then only once the motor has reached its full speed do you then close the valve and increase the load on the machine. So some constraints or some considerations that we need to take into account when designing a low inrush current motor. These are the design considerations that we aim for. So in general, what we're aiming to achieve is a locked rotor current of 3 to 4 times the nominal rating, we want to achieve a locked rotor torque of at least between 0.25 and 0.35 per unit of nominal. Our breakdown torque needs to remain at least at 1.5 per unit or greater. The main reason for that is once you accelerate a machine and it gets to full speed, if you endure a voltage drop at the motor terminals in steady state conditions, it is the breakdown torque that gets used up in order to continue running without stalling. So the standards prescribe 10 to 15% voltage drop. The motor still needs to run the load. If we were to drop the breakdown torque to below 1.5 per unit value, it would be very difficult to not stall during voltage drop conditions of more than 10 to 15%. From an efficiency point of view, we're aiming for, on these large motors, typically more than 96%, power factor more than 88%, and as mentioned, a transient voltage drop in steady state condition of 15% or less. So in essence, we want to design a motor that has a lower starting current, but we want to maintain the performance advantages of a normal squirrel cage machine, and that is high performance, robust solution, low maintenance, and keep it cost effective. So when we're designing a low inrush current motor, the challenge, as I already indicated, is to bring down the locked rotor current represented by the first equation on the top. But at the same time, we need to maintain a breakdown torque of at least around 1.5 times or greater. The problem is these two design parameters are linked. When we are reducing the locked rotor current of a machine, we need to reduce both the stator and rotor reactance in order to decrease the locked rotor current. At the same time, breakdown torque is affected by those same two parameters. And so you'll see on this graph here, what we did was we took a number of different motors that we have manufactured over the years, and we plotted them to determine the relationship between these two parameters. There is some spreading because there is some design considerations in these constants, Ki and Kt, that can make improvements between the locked rotor current and the breakdown torque. These include things like playing around with the magnetic core dimensions, the stator and rotor slot combinations and shapes, as well as the number of winding turns. However, these only have a small effect on this relationship. By far the largest effect is the decrease of the reactance of the stator and the rotor. What this means in practicality is that we get to some physical limit. In other words, it is impossible for us to drop a motor's locked rotor current or starting current below a certain value without starting to impede the breakdown torque. We found that physical limit to be close to the 3 times starting current condition. Physically quite difficult to achieve 150% of breakdown torque with locked rotor current lower than 300%. Okay, this just shows some of the things that we can do from a design consideration in order to reduce the locked rotor current of the motor. We won't go into detail there. Our time is running. So let's take a look at a real life example. This was an application for a very large machine, a 10 megawatt. This particular plant, in fact, this was for an oil platform in the sea, and there were some considerations that we needed to meet. The client had specified that he needed a medium to low impact on his power supply system, and he also had some fairly high steady state voltage drops. Right, so this is the machine that we designed, and we created some design parameters that we wanted to meet in order to meet the requirement of the client's specification. Our starting current needed to be as low as possible without introducing any other types of starting methods. So our design was for a starting current of around 3 times. We achieved 3.18. Locked rotor torque, we wanted 0.37. We achieved 0.4. Breakdown torque 1.48, and we achieved 1.48. So really, this motor was literally on its limit in terms of how low we could get the current on a standard design squirrel cage machine. Then before it left the factory, we wanted to test that the machine can operate within the parameters that were prescribed. So what was the parameters that were prescribed to us was that this machine needed to start at an 80% voltage drop, and it needed to accelerate the load to full speed, but it was only a partial load at full speed. Once it reached full speed, the voltage would return to 100% of its value, and then the load would be increased to 100% of nominal load value. And then after it started, another large motor would be started on this oil platform, resulting in a 15% voltage drop, and this motor needed to continue to operate without stalling through that voltage dip. So just to go through this quickly, the green curve is the voltage, the blue curve is the load, the red curve is the motor torque. So you can see the motor accelerates the load, which is the blue curve, to a lightly loaded condition, 30% of rated, and then the voltage returns from 80% to 100% of rated, at which time the load is increased. After running for some time, another large motor starts on the platform, and we have a 15% voltage drop, during which case the machine suffers a slight dip in speed, which is in black, but continues to operate without stalling. Okay, just to close this section off, we have a technical and economic comparison of the large motor designs. I've just focused on 3 of them to save time, but we've used the induction motor direct online as our reference, and we've compared against the parameters of impact on power supply, weight, inertia, footprint, power factor, and efficiency. You can see that if we make that reference as 100, if you compare it to a low inrush current induction motor, the impact on the power supply is obviously reduced. So we put that at 60%. The weight is slightly more because we need more active material in order to decrease the current, basically to increase the reactances. The inertia is slightly higher because of that additional material. Our footprint is slightly higher, but very similar. And the power factor and efficiency is slightly less, but very, very similar. And then I've just highlighted the same comparison for a low inrush current synchronous motor. We can do the same design considerations for synchronous machines. These would give the same advantage in terms of impact on the power supply. However, your weight would be significantly higher, as well as your inertia. Your footprint is almost double. Of course, we have a big advantage on a synchronous machine in that we can manipulate the power factor. Our efficiency is slightly better, but for the additional capex for a synchronous motor, it's not always a payoff benefit. Then our last comparison would be against capex, opex, complexity, and adaptability to starting conditions. Again, we use the induction motor direct online as our reference, and we can see that a low inrush current design motor is approximately 20% more in the case of capex. Opex is pretty much the same as with complexity and adaptability to other starting conditions. A synchronous machine of similar design would be more than double the capex. Opex would be slightly more. It is a much more complex machine, and it has a little bit less adaptability to starting conditions. There is much more information, much more detailed on the low inrush current design considerations in this IEEE paper, which we can send you details of when you get the YouTube link. All right, so we get now to item 6 on the agenda, large industrial drive systems. Okay, so these are pretty common knowledge to most engineers. Why is it important to select a proper starting method for large motors? Well, voltage drop, when you have a voltage drop at the terminal of a motor, the torque decreases to the square of that voltage drop. So this is something to consider. Also, when a large motor starts on a plant, you can induce a voltage drop on other machines and loads on the grid, on the plant at least. Prolonged start can cause the rotor to overheat. So you need to examine the thermal capability or the thermal limit of the machine. And then multiple direct online starts can develop a high mechanical stress. So it's something that needs to be taken into consideration. And then overload of local generation. This talks to the power supply issue for the plant. Right, so I'm showing why it is so important on medium voltage motors to do a specific analysis of a start condition. Why you need to take more design consideration into or analysis into consideration, and that is because on low voltage machines we supply them off the shelf. They are generally designed with very high starting torques and very high breakdown torques, because they need to cover a multitude of applications without specific analysis for each and every application. However, a medium voltage motor, because of the expense of the material and the expense of a medium voltage machine, we design them a lot closer to, or a lot finer in terms of their application. And so it's much more important to do a specific analysis to make sure that the motor can get the load away. Especially so when we have a constant torque load like a conveyor or a mill, it becomes a lot more imperative to do the starting studies properly. I'm going to speed up because I see our time is running a little short. I think we have about 30 minutes left, but we need to include some time for questions. Okay, so some main considerations to avoid bad starting. Consider the application characteristics. This we've discussed already. Torque, load inertia, frequency of starts. We need to analyze the power supply. This is important from a voltage drop point of view to determine how much of a starting current can be provided by the grid without causing an issue for other loads. And we need to verify the motor characteristics, specifically looking at the inrush current, the torque of the machine, and the available thermal capacity of the machine. All right, so these are also common knowledge. We're just summarizing some of the starting methods for large machines. So full voltage starting is either a low inrush current design motor, which we've discussed, or starting a standard squirrel cage machine direct online. Reduced voltage starting is making use of an indirect starter added to the circuit. In this case, the example is reactor, auto transformer, or solid state soft starter. Capacitor assisted starting, captive transformer starting, not so common, and then variable speed drives as starting methods and speed control. What's interesting is that at least 63% of motors in the field are still started direct online. You can see VSDs are increasing, but currently sits at about 14% of motors installed. Okay. Again, this is something that is common knowledge from an engineering point of view in most cases, but let's just cover the basics. Direct online starting has the following advantages: low capex, basic and simple design, low maintenance, simple training requirements, highest starting torque possible without the use of a VSD. I think I need to just put a disclaimer there. Also, you can use a slip ring machine or a wound rotor induction motor with an external rheostat. Some disadvantages to direct online starting: mechanical stress is extremely high, especially on very large motors, the kind that we are talking about in this presentation. You get a very high inrush current, so the power supply network needs to be able to handle a high impact start. And then some other issues: voltage sag goes along with the high inrush current, voltage flicker, large power transformers needed if you've got a lot of large direct online line loads starting, fault capacity, and driven load shock that also talks to mechanical shock during direct online starting. Okay, soft starting. I'm not going to go through that in detail, but essentially we can use a soft starter in circuit with a standard squirrel cage machine to reduce the voltage. Obviously, one thing to be aware of is that when you reduce the voltage to the motor terminals, the torque is reduced to the square. So it is not suitable for every application, and a very in-depth detailed check needs to be performed to ensure that a soft starter can work in a specific application. Right. The next starting method that we're going to look at is MV drives. So of course, this is the best starting method possible. However, from a capex point of view, it is expensive. But your starting current to starting torque ratio is, depending if you size the VSD correctly, is arguably the best of any other starting method. Okay, as with a wound rotor, induction motor, and rheostat, if you size the VSD correctly, the only limitation to start up torque is the breakdown torque of the machine, and you can achieve this throughout the entire speed range during startup of an induction motor. Right. These two different topologies, we're showing a neutral point clamp topology here, and on the next slide we're showing a cascaded H-bridge topology. I'm not going to go into detail in this part. In part 2, next week Thursday, we'll go into a lot more detail in terms of these two topologies. We'll examine them specifically in more detail. Right, I've just put a summary, which again is not something I'm going to spend a lot of detail on. Most people know this. It's just some design criteria compared to which starting method is the optimal to choose for a certain situation. For example, if I need a high starting torque, I would either go direct online or VSD start. Of course, a soft starter is not going to give me a high starting torque. If I need speed control, obviously my only option there would be a VSD. Of course, there are alternatives using a wound rotor induction motor with fixed brushes, but this is just to simplify these three main starting methods. All right. If a power plant or if an industrial plant can handle a high capacity, high impact starting current, in other words, if there is a high capacity power supply, direct online is arguably your best option, depending on other considerations, of course, like mechanical stress and strain on the equipment. For medium capacity power supplies, a soft starter or low inrush current design motor is a good option. This just shows the topology of of a typical medium voltage large soft starter. Okay, if we are using a VSD for full control, in other words, the VSD is permanently connected to the machine for both starting and operation, then a typical topology would look like this. We have a phase shifting transformer or an integral transformer, the VSD, and a motor. The VSD would need to be sized according to the motor and the load condition, because it is connected permanently into the circuit. However, we do have the option, and this is possible if you want to use the VSD only for starting, and it does not need to be permanently connected to the machine. So we are able to start a machine with the VSD and bypass the VSD. So the VSD can be provided with a built-in synchronism card or sync relay that is able to synchronize the VSD voltage output with the supply voltage output, and we can do a bypass. In this case, there are a few milliseconds where both the VSD voltage and the supply voltage is applied to the motor before the VSD is taken out of the circuit. So one practical application for this would be if you are using a VSD to start a motor that does not necessarily get to its full torque at the end of acceleration. It was the blue curve that I showed earlier. And it is theoretically possible to put a VSD in circuit that is smaller than the rating of the motor, just to get the motor up to speed, and then bypass the motor before the full load is applied. Another application where this is useful is if you want the advantage of starting motors and loads with a VSD, but to reduce the capex, you can install one VSD and start multiple motors. This is useful, for example, if in pump or fan applications where you do not necessarily need to vary the speed of all the pumps or all the fans. So you can still start those fans or pumps with the VSD, bypass each one of them once they are started, and then keep one in circuit, for example, to adjust your flow rate on PID control. We can do the same technique, but add in some redundancy, just in case there is an issue of reliability. If there's some concern there, we can do a similar control method, but putting two VSDs, just have one as a backup, in other words. So here we have an example of starting motor 1 with the VSD, bypassing that motor. And then we can use that same VSD to start multiple motors. Okay, just to show you some different methods of using a VSD connected to a motor. So in this case, we have a large single VSD permanently connected to the motor. But we can also we can move the complexity from the VSD to the motor. This is an example of an application where the motor had double windings. We had one VSD supplying one winding and the other VSD supplying the other winding. So this particular application, it's not very common, but it was used it had two different load profiles. So in one load profile, we would energize only one winding, and only when the load demand from the process increased would we need to energize both windings of the motor. All right, here's an example of using multiple VSDs for multiple motors. So one example of using this type of configuration would be on a tandem load. Let's say, for example, a dual pinion mill. We are able to run one motor with one VSD, one motor with the other VSD. And we can, there's some benefit to that in terms of the phase shift transformers. We can increase the harmonics. Okay, I went through that rather quickly, so just trip me up. But this is really the point that I wanted to get to. So earlier on, we discussed the certain load condition where you do not get to the full load condition at the end of the curve. So I want to talk about a novel use of a VSD, where you can use the VSD only for starting. So in some applications, for example, certain compressor applications, it is possible to start the machine with a VSD. This would be in cases where you want to have the advantage of starting the load with a VSD. In other words, you want a very low impact to your power supply system, but you accelerate the load up till the end of acceleration, and the full load is not yet applied. So this curve you recognize from earlier. We have the blue curve, which is a load that accelerates up to the end of acceleration, but is not the full load is not necessarily yet applied. In this case, the motor would need to be designed for the full load condition. However, it is theoretically possible, or it is practically possible, to design the VSD, if it is only used for starting, at a reduced rating. So from a CapEx point of view, this can dramatically reduce the outlay or the cost involved. Okay, let's get into the details of a start of this nature. All right, so we are able to start the load with the VSD. Remember, we are using a VSD that is smaller in capacity than the size of the motor. So in this case, we start the load and we ramp up the speed, which is shown in blue, and the motor voltage is ramped up linearly in proportion to the speed. Once we get to the point of nominal speed and nominal voltage, we then apply the bypass. The VSD can be or is supplied with its own integral synchronous bypass relay. And so we have a period of synchronization that occurs. And when we reach synchronization, we are able to close the bypass switch for a few milliseconds. Both the VSD and the supply is providing voltage to the motor, whereafter the VSD switch is opened and only the power only from the supply is connected to the machine. It would be at this point that the full load can now be applied to the motor, whether through valves or vanes or other method. Sorry. Okay, here's a specific example of what I'm talking about. So in this case, we had a reciprocal compressor. The motor rated power was 7.6 megawatts, and the supply voltage was 6 kV. We were able to, in this case, because the end of load curve was dramatically reduced compared to after acceleration when the load is applied, we were able to start this load with a VSD rated 800 kilowatts. So we're talking about a 7.65 megawatt machine, but using an 800 kilowatt 6 kV VSD to start that load and ramp it up to speed. Okay, so that was one example of optimizing a startup using a smaller drive, but rated at the same voltage. We can go one step further and actually start a machine with both a smaller rated VSD and a VSD with a lower voltage output than the supply voltage. Of course, there are a lot of design considerations that we need to take into account. But essentially, this is what we do. So the reason that we've selected a VSD in this case that is both smaller in its rated power than the motor, as well as a lower voltage, is purely from a CapEx point of view. So if it is cheaper, for example, to use a 3.3 kV motor or a 4.16 kV motor, a VSD at least, you can use it to start a 6 kV machine. Again, provided this is a light starting duty application that does not get to its full load condition at the end of acceleration curve. In this case, we are able to start the motor. We can see that we ramp up the speed to full speed. However, the voltage output of the VSD is at some percentage below the nominal voltage of the motor itself. After reaching full speed condition at reduced voltage, we can bypass the VSD. In this case, I cannot synchronize and close both switches simultaneously because of the difference in the voltage output of the VSD and the supply voltage. So I have a momentary period where the VSD output switch is open. In that time, the motor voltage starts to drop. I then have a small window in which to apply my synchronism and close my bypass switch. Here is a specific example. In this case, the rated power of the motor was a 12.7 megawatt, and the supply voltage 6 kV. However, if you look at the load torque curve, at end of acceleration, we only need to apply somewhere between 20 and 30% of load, and only after acceleration is the full load then applied. One other consideration here was the voltage drop requirements. In fact, one of the main reasons that they used a VSD to start this compressor was because they could not handle a high voltage drop, and the power supply was fairly low capacity. So if we look at, we made use of a 12.7 megawatt motor, but the VSD rated power was able to be reduced to 3.6 megawatts and at a reduced voltage of 4.16 kV. And the main reason for doing this is a 6.6 kV VSD would be much more expensive. So we were able to make use of the fact, or able to make use of reducing the VSD's power rating, as well as dropping the voltage. Of course, we need to calculate very carefully that the two in combination, because both will result in a reduction in torque during the startup of this machine. But we need to evaluate both together in order to ensure that we can get this load away. And here's an actual measurement of the startup of this machine, and then the bypass from the VSD to the supply. So we can see here, our green graph is the VSD output voltage. The RMS value, although it doesn't look like it, is lower than the yellow graph, which is the supply voltage. And the purple is the motor current. So when we are operating, when we started the motor with the VSD, we ramped it up to full speed, and this is the output voltage. Then after some time, we want to close the bypass switch. We first need to open the output, the VSD output. The motor maintains some voltage even though the VSD is switched off in this time frame. And after some time, at this point where there's a small current spike, that is when we close the bypass switchgear. So we do get a small current spike because our motor voltage is sitting at approximately 4 kV and our supply voltage is 6 kV. However, the current peak or the current spike during that transition is not more than about 1.5 times in this case of motor nominal current. So still a lot lower than a direct online situation. And then after some time running online, that current settles down to full load current value, and then the full load can be applied to the machine. Okay, so I've got a video just showing the actual measurements of a bypass scenario, and I'll just talk you through it. So let me just pause it here for a moment. So we have the yellow. The yellow is the supply voltage. The turquoise or purple is the output voltage of the VSD, and the purple is the motor current. So you'll see we are supplying the voltage to the motor from the VSD only. The synchronism relay is trying to find synchronism between the supply voltage and the VSD voltage. It's hunting, trying to search for synchronism. Now we've found synchronism, so now we can close the bypass contactor. Right, then I think Theo, how are we doing for time?
No, Kirk, we've got some time. I know you're close to the end, so we can then open up for questions. So I think don't talk too much.
Let me go through the next the next section. So essentially what we've discussed is a novel way of starting motors in circumstances where you want to apply a VSD to the start in order to get the benefits of starting the machine with a VSD, but where you are not using the VSD permanently connected to the machine, and that I've already mentioned, is for applications where your end of curve load torque on your motor is less than the load torque applied after you get to acceleration. We can do exactly the same on synchronous motors. I'm not going to go into too much detail. Essentially, it is the same with one small difference, and that is when we during synchronization, we have separate excitation control on the field winding of the synchronous machine. And so we can actually use this to our advantage. So previously we looked at two scenarios where we have a reduced VSD size to start certain motors, and the condition where we have both a reduced VSD size and reduced voltage to start certain applications. In the case of a synchronous motor, we can make use of a reduced size VSD with reduced voltage and use the excitation control to actually benefit us and increase the voltage before we do the bypass. Let me show you what I mean. So in this case, we can start the motor using the VSD, and we can ramp up the motor to nominal speed, but reduced voltage output from the VSD. We have applied excitation to the field of the synchronous machine. Now we want to do a bypass. Because of the inertia of the synchronous machine, we overspeed the motor slightly just to allow us a bigger window of synchronizing when we want to do the changeover. So in this case, we can disconnect the VSD from the motor just before we want to achieve bypass. We use the excitation control to increase the voltage on the machine. You can see that the speed of the motor starts to decrease due to its high inertia, but we have increased the voltage purely using the excitation controller to get to nominal voltage. Then we synchronize the supply voltage to the motor voltage. We have a certain window within which to do that. And then we can close the bypass switch. This was an actual test or measurements that we took in our laboratory. So this just shows what that transition looks like between the running on the VSD and bypassing to the supply. So during this first phase, we are supplying a reduced voltage, which is in green. A reduced voltage, the yellow is the supply voltage. So we can see there's quite a dramatic difference between the VSD output voltage and the supply voltage. And the blue represents synchronism, our synchronous scope. If it's at 0, it means it's in sync. If it's at 1, it's out of synchronization. Then we move to the second phase, where we remove the VSD from the circuit, but use the excitation control to increase the voltage of the motor. That is why the green voltage is increasing to meet the supply voltage rating. Then we are searching for synchronism between the supply voltage and the motor voltage. And at this point, synchronism has been obtained, and we can close the bypass switch. Just to show that same bypass in terms of what it does to the current. This is the motor current during the VSD startup and run phase. The current then dramatically reduces when we open the VSD output, and increase the voltage from the excitation. And then at the point of synchronism, there is a small increase in current when we bring in the bypass contactor, but it is not more than the full load current of the machine. Okay. Some of the advantages to this kind of starting method, we're essentially using the VSD to start the motor with a very, very low impact on the power supply. It also allows the use of reduced voltage devices, and that is, from a CapEx point of view, is the main consideration there. It avoids complex starting coordination, avoids oversizing mechanical equipment, reducing installation costs, reduces torque ripple that can cause torsional vibrations. Why? Because we can ramp up, we can set the acceleration time in the VSD, and we can ramp up the motor very slowly if we need to. Usual motor heating problems during startup are not experienced with VSDs, again, because we can control both the starting torque and acceleration time. It eliminates the constant refurbishment work on the motors, considerably decreases maintenance and inspection intervals. Okay, then just to summarize, we look at some parameters for the different starting methods that we've discussed. So when we start and transfer with the VSD and bypass, our power factor is approximately 0.8. We have a very low inrush current at the mains. Our motor rated current, okay, let's look at it like this. This is comparing the start and transfer with a VSD on an induction motor, and this is looking at the start and transfer VSD bypass on a synchronous machine. Essentially, your power factor would be worse on an induction motor than it would on a synchronous machine. Your inrush current would be similar. Footprint would be similar. Your motor rated current is slightly reduced on your synchronous machine, but your capex would be much higher. Sorry, I think there's actually a mistake here. No, that is correct. Sorry, I think I need. Okay, just to bring this into
the end of the previous slide, sorry.
No problem. Oops, sorry. So I think let's bring this into a landing. Conclusions. The most cost-effective solution for the drive system depends on the load characteristics and power supply capabilities. In the majority of cases, the squirrel cage induction motor is the most optimized solution, except when reactive power is needed. When a synchronous motor is needed, the cylindrical laminated rotor, combined with or without VSD starting, becomes the most cost-effective solution. Voltage source inverter VSDs provide significant advantages in comparison with classical topologies and flexibility for starting large motors. Having the ability to analyze, engineer, and manufacture in the same place is a great differential to provide optimized solution for large motors.
Thanks, Kirk. Everybody in the attendees list, I just want to open the questions again. But if anybody has questions, you can either raise your hand and we can see if we can unmute you, or alternatively, if you can pose your question in the question section of the control panel, that would also be great. So while we wait for that, Kirk, myself, I've got 2 questions. Granted, not the most sophisticated questions, but something that struck a nerve when you were going through the presentation for me. Specifically, life cycle impact on these large motors when running them continuously with a VSD, compared, obviously, for a similar application where you've decided to utilize VSD for the possibility of speed control, but not necessarily required. What would be the life cycle impact on the motor that's direct online versus VSD operated?
I think that depends very much on how many starts you would be applying to a direct online motor. One thing to note on these very large motors, because of the size of the rotor, you wouldn't believe when the amount of stress and strain that is placed on the machine during a direct online start. You are banging full voltage onto the terminals of that motor, and in other words, the stator magnetic field is rotating at the supply frequency of 50 hertz or 60 hertz, and the rotor needs to play catch up. That puts a massive mechanical strain on the rotor. So when you apply a VSD, if you are doing multiple starts, your VSD can ramp up that rotor over a prolonged period of time. So arguably, that is actually going to improve the life cycle of your electric motor, especially in the case where you're doing multiple starts.
So then, would a further improvement then actually some of the slides where you showed the bypass contactor, we're then essentially getting that benefit of the soft starting, if I can put it that way, and then a bypass contactor that for the running duration, you wouldn't have the harmonics on the motor during normal running.
Correct. So unfortunately, I rushed through that section a little bit just because I was a little tight on time. But essentially, it's arguable. So what we covered there was if you have an application where you want to apply a very low impact on the motor during starting, and also a low impact on the power supply during starting, a VSD is one of the options to do that. But it is not traditionally only for starting. The normal tendency is to use the VSD for starting and operating when you only when you need permanent speed control. So we just took a little more of a novel look at that, at certain applications where you do want to get the benefits of starting the machine with the VSD, but you don't necessarily want to use it for speed control. So it does help to extend the life of the machine, especially when you are doing multiple starts. But then the added benefit is, in some cases, you are able to actually use a VSD that is rated smaller than the rating of the motor.
Agreed.
I think that is the main principle I wanted to get across there.
Awesome. Then the second one on the pony converter, the benefit of that starting method from a capex point of view, I'm assuming is again, you can reduce the size of the VSD in terms of the voltage rating of the VSD as well as the megawatt rating of that VSD.
Correct. So on those 2 applications that we looked at, the one, for example, we had a 7 megawatt motor, but we were able to use only an 800 kilowatt VSD to get that motor away. And we taking advantage of the fact that this is a low start duty application where your locked rotor torque requirement is sort of, about 30% of the motor rating. And when you get to the end of that acceleration curve, you only need to apply less than 50% of the motor rated torque. And so we use that. In fact, on that example, I think we only needed to apply 20 to 25% of the motor rated torque at the end of acceleration. And so you're putting in a VSD that is much, much cheaper than if you had to put in a 7 megawatt VSD. So you're getting the advantages of all the advantages of starting with a VSD, but then you bypassing it before you apply full load condition.
Because I know a lot of people's concerns are for the permanent operating off of a VSD, as well as the harmonics injected into the motor circuit.
Yeah, so yeah, that is a separate consideration, but I guess we need to weigh up what is worse for the motor. And remember, it's only seen in the pony converter. It's only seeing that harmonics during starting. So the harmonic output from the VSD on the motor results in a slightly increased thermal temperature rise, but that is mainly a consideration during steady state condition. It's not applied for long enough during starting to really have a considerable impact on that on the thermal increase of that machine. The other implication would be peak voltages on the insulation. But that's something that just needs to be taken into consideration, either ensuring that the motor insulation is rated sufficiently high enough for those peak voltages, or alternatively putting a filter on the output of the VSD or some sort of a reactor just to keep those at a minimum.
Okay, awesome. That's it from me and my limited capabilities. We have some questions in the forum. The first one's a compliment to you from Rolf Jonker. Just wants to say it's a very good presentation, that he enjoyed it a lot. Then the first question from Sibonelo is, what causes the electric discharge in the motor and how to prevent it?
I'm assuming that is talking. I wonder if that's talking about a synchronous motor.
Okay, Sibonelo, maybe if you can just elaborate on your question. I'm just going to move on so long to the next one. We'll come back to yours. What
Unless you're talking about partial discharge or corona.
Yes, that's immediately where I went as well, Kirk, is PD.
Okay, so corona effect and partial discharge. Look, that's a condition that can affect a motor, both a direct online motor and a motor operated on VSD. And it's generally caused by a high DVDT. In other words, a very fast change in voltage with respect to time. And it often affects the first interturn insulation. And it is especially, it can especially be an issue on VSD applications. But not necessarily. It's also a consideration for high voltage motors, 11 kV. Even on direct online. So that also talks to one of your questions regarding the harmonics and peak voltages to the motor. So we need to ensure that the DVDT from the VSD is limited so that it does not, or so that it prevents as far as possible from this partial discharge or corona effect from occurring on that first insulation interturn.
I think that also comes down to ensuring that the motor is suitable for VSD operation.
Correct.
So the next question is from Christian. What are the risks associated with reduced voltage starting by using an auto transformer?
So look, for me, the biggest issue is when you, so let's maybe answer this in this way. Let's look at two examples of reduced voltage starting. One is an auto transformer start, and one is a solid state soft starter start. And let's maybe just do a very high level comparison of the two. Your risk on a auto transformer is that you specify certain tap settings, okay, and you are limited then to those levels of voltage taps to your motor. If for any reason between design and actual application on site you have some difference in the parameters from design to actual operation, you can get a little bit snookered. Let's say, for example, you slightly underestimated the load torque curve, and so your highest tap setting on the auto transformer does not allow you sufficient torque to get that motor away. You are completely snookered. You would need to make a new auto transformer. Whereas if you use a solid state soft starter, you've got a lot more flexibility. You can increase generally on medium voltage, high powered soft starters, you can alter the starting current anywhere between 0 to 90% of the motor's starting current. So for example, if you've got if the machine has a starting current of 6 times its nominal, you can essentially, on a soft starter, if you are struggling to get that load away, you can set it right up to 5.5 times, for example. So it just gives you more flexibility in case there were some mistakes made between design and actual application.
So in the end, you need to ensure that you've got, how can I say, as accurate as possible information at design stage when you go that route, to ensure that you don't come up with any hiccups during commissioning.
Correct. There's one additional issue, and that is you're jumping from one tap setting to another. It's not a smooth transition. Or you are starting just on one tap setting, and then you are bypassing that auto transformer once the machine gets up to speed. So that switching either between taps or bypassing from the auto transformer to the line can result in a current spike that, again, when compared to a solid state soft starter, you would not get.
Agreed. If we look at it from a positive point, though, auto transformer much simpler to implement.
Correct. Much simpler to implement, but normally on a solid state soft starter, you've got a standard design, whereas an auto transformer is normally custom designed for its specific application. The soft starter, in its standard design, it already incorporates the thyristor, a contactor that brings the thyristors into circuit, and then once the motor is accelerated up to speed, it has a built-in bypass contactor that bypasses that soft starter. On a auto transformer, that all needs to be manufactured and coupled together separately.
But from a cost point of view, sorry, I'm going off on a tangent now, but from a cost point of view, going the auto transformer route, if you do the design correctly, versus speaking of, for argument's sake, of 11 kV motors, going the soft starter route versus going a thyristor soft starter, how would those two compare from a cost point of view?
I would hazard a guess that the cost is not as different as what you would think. If you compare a soft starter to a VSD, there's a massive difference in price. So I would suspect that if you did a comparison between a solid state soft starter and an auto transformer, you would be a lot closer. And yes, the auto transformer would be cheaper, but you'd be a lot closer in capex than what you probably think.
Okay. No, awesome. I see Christian is happy with your answer. So Simonella, I haven't received an update on your question, so I'm assuming that the way Rolf, sorry, I'm reading Rolf there on the screen, Kirk. The way Kirk answered it was to your satisfaction. Kirk, that seems to be it from the questions. Then just because the one question is pertaining to this, the material will be uploaded to, the whole presentation has been recorded, will be uploaded to YouTube probably within the next few days after it's been edited. And it'll also be loaded onto the SAIEE website, so you'd be able to get access to this material, Mavinga. So don't worry about that. Then, yeah, everyone, thank you for attending the webinar. Please do visit the SAIEE website on www.saiee.org.za for any of the upcoming webinars. We will also join us next week for part 2 of this series, where Kirk will go into more detail regarding the drive systems as he hinted towards today. Then, Kirk, and just a special thanks to yourself, as well as Joe Martins for the effort in arranging the webinar, and there's a lot of work that went into these presentations. And then also to Minx for all the effort with the marketing materials and arranging the webinar platform. And then Kirk, if there's anything from yourself or Minx or Joe, I think we can end if you have nothing else to say.
Thank you very much. Just apologies, I had to rush through that one section just because I saw the time running away a little bit. But the information will be distributed in the actual PowerPoint or PDF version of the presentation.
Okay, thanks. Cheers, everyone.
Cheers, thank you.